Okay, so what if I told you there are hidden rules that control all life on Earth? I'm talking about a kind of Newton's laws, but for biology. These principles explain why some populations explode and others vanish, and they might even tell us something about our own future. And our story begins with a ghost.
To really get these rules, we have to start with that ghost, the passenger pigeon. Picture this. It's 1813, and the famous naturalist John James Audubon sees a flock of these birds so huge, so dense, that it literally darkens the sun and takes 3 whole days to pass. He figured there were over 1 billion of them. Now, fast forward just 1 century, to 1914, the very last passenger pigeon on Earth dies, all alone in a zoo. Gone. Forever. So that's the big mystery, right? How on earth does a population of billions just disappear in what's basically the blink of an eye, ecologically speaking? It feels totally chaotic, completely random. But what if it wasn't? What if a collapse that massive actually followed a predictable, almost mathematical set of rules? Well, that's exactly what ecologist Peter Turchin argued. He said that, yeah, there are foundational principles for this stuff. Think of them like Newton's laws of motion, but for living things. These laws give us a powerful framework for understanding the rise and fall of every population, from pigeons to people. All right, so let's break these rules down, starting with the first one. This is the big one, the default setting for all life. It's the engine that drives pretty much everything else. Turchin calls this the exponential law. And you can really think of it as biology's version of inertia. You know how an object in motion wants to stay in motion? Well, a population that's growing wants to keep growing. And not just growing, but growing faster and faster and faster. This is the baseline impulse that's hardwired into every living thing. Make more of yourself. But, as the passenger pigeon showed us all too clearly, this exponential party never ever lasts forever. Something always gets in the way. And that brings us to the crucial second rule. So, what is this powerful force that pushes back against endless growth? Is it some outside enemy? A meteor? Nope. The most powerful limit actually comes from within the system itself. And this is the law of self-limitation. It's really simple when you think about it. As a population explodes, it starts to run out of stuff. Food, a place to live, you name it. So growth naturally slows down, and then it stops. That ceiling, that maximum number an environment can possibly support, is what ecologists call its carrying capacity. Now, the engine driving this self-limitation has a bit of a fancy name: intraspecific competition. All that means is individuals of the same species are competing against each other for the same limited resources. I absolutely love this analogy. The ecologist W.J. Sutherland compares it to drinking the pub dry. I mean, it's perfect, right? When the pub opens, the drinks are flowing, everybody's happy. But as more and more people show up, eventually the taps run dry. There's just not enough to go around for everyone. And here's where it gets really interesting. This competition doesn't just put a cap on numbers, it can shape the evolution of a species in the most incredible ways. For a perfect and kind of wild example of this, we need to meet the horned beetle. Check this out. Depending entirely on how much food it got to eat when it was just a little larva, a male horned beetle can go down one of two totally different life paths. If it was well-fed, eat like a king, it grows up to be a huge armored garter with these massive horns. But if it was poorly fed, it becomes a tiny hornless sneaker male. Now, both of these guys have the exact same goal: find a female and mate. But their playbooks could not be more different. The garter is all about brute force, fighting off other males. The sneaker, on the other hand, is all about stealth. He doesn't fight at all. He digs these secret side tunnels to sneak right past the big guard. And for him, horns would be a total liability. They'd just get in the way and give him away. It's a perfect example of this internal competition driving evolution. So we've got the impulse to grow, and we've got the internal limits that push back. But of course, populations don't exist in a vacuum. They're all interacting with each other. And that brings us to our third and final rule. This one is called consumer resource oscillations. It sounds complicated, but the idea is actually this beautiful rhythmic dance. It means that the lives of predators and their prey, or grazers and the plants they eat, are totally locked together. When the prey population booms, the predator population booms right after it. But when there are too many predators, the prey population crashes, which of course means the predator population is going to crash too. It's this endless cyclical dance of boom and bust. And if you want to see this dance in action, there is no better real-world example than the incredible decades-long study of wolves and moose on Isle Royale. It's this isolated island in Lake Superior, basically a perfect, self-contained natural laboratory. The whole story of this island is just this perfect drama of cause and effect. So in the late 40s, wolves make their way to the island and find a moose paradise. So their numbers soar, peaking at about 50 wolves in 1980. But then, disaster. A virus, probably from a visitor's dog, just devastates the wolves. So with their main predator pretty much gone, what do the moose do? They have a party. Their population explodes to 2,400. But then they eat themselves out of house and home, and the population crashes from mass starvation. It's a tragic but perfect example of this oscillation. So, there you have it. Our three laws: exponential growth, self-limitation, and the great dance of oscillation. They apply to pigeons, they apply to beetles, they apply to moose, which, of course, leads to the elephant in the room. Do these rules apply to us? Are we, Homo sapiens, bound by the same ecological laws as every other living thing on this planet? Or have we somehow broken free? This is honestly one of the biggest and most important debates in all of science. And the stakes couldn't be higher. Just consider this. Back in 1850, there was about 1 billion of us on the entire planet. By 2003, there was 6.3 billion. I mean, that graph looks an awful lot like rule number 1, doesn't it? Unchecked exponential growth. So the question is, will rule number 2 inevitably kick in?
You've basically got two major camps in this debate. On one side, you have the ecologists. Most of them would say, look, self-limitation is inevitable. We're a biological population, period. We will eventually hit our carrying capacity. But on the other side, you had economists like the late Julian Simon. He argued that human ingenuity is, quote, the ultimate resource. He believed that we would always innovate our way out of any shortage, essentially raising our own carrying capacity whenever we needed to.
So here's where we land. We figured out the fundamental rules of the game for all life on this planet. We know how it's played. The question that's going to define our entire future is this: are we just another player on the board, bound by these ancient, unbreakable laws? Or are we the one species that can actually figure out how to change the rules of the game itself?